Okay, so last time we discussed the states of the string, of the open and closed string in light cone gauge. So I'll remind you a little bit what we finished with. So we finished with closed string states. And in the case of closed string, so the mass formula is slightly modified. And one has the level matching condition that which says that so here we have alpha and A and alpha tilde and A oscillators that can create string states in the Fock space of these oscillators. And so the level matching condition says that n is equal to n tilde. This came up from integrating the x minus prime with the sigma, saying that this is periodic, so this is 0. Came from this condition. And well, we discussed some lowest levels, so one still has a tachyon at level 0. So so we have here a tachyon. This is n equals n tilde equals 0, which was q squared minus m squared equals 8 pi t. And then one has the level 1 states. So this is so here one has and here q squared is 0. So these are massless states. So these are massless states, and as we discussed, they describe some generalized gravity multiplet. So they can be symmetrized, anti-symmetrized. There can be also a trace. One can take a trace, and so this corresponds to the in field theory. This corresponds to the graviton, the anti-symmetric field, and then the dilaton, which is a scalar particle. These are massless states of the closed string, closed bosonic string. And this is an important relation because this is the general property of closed string theory, that it has a graviton in it and possibly some other massless fields. So in case of the superstring, there is no tachyon, like we discussed. So the constant A, the normal ordering constant A, should be set to 0 there, basically due to supersymmetry. But then there are still the massless states are still present, and they are the graviton and its supersymmetric partners in the superstring.
So if there's a q squared equal to 8 pi t is the mass of which is m squared of which particle? Tachyon?
Yeah, tachyon, yeah. It's m negative of m squared, yeah.
But 8 pi t shouldn't it be negative?
Yeah, the mass squared is negative, yeah. It's minus m squared. Right? N equals 0. So A is 1. M squared is minus 8 pi t, yes. So yeah, as you recall, we derived that A is 1 and by Lorentz invariance. Well, also we discussed last time the growth of string states for the open string. So for the closed string is similar because the closed string Hilbert space level n just that's a product of open string states. So the number of states level n is what we call pk24 squared, and it grows as square root of alpha prime times m closed seven times. So again, exponential growth with the mass. So Hagedorn growth. So yeah, you can also write out the various multiplets that arise at various levels, and in textbooks you can find the corresponding tables. They get pretty soon they get quite involved, and you can see that actually SO24 multiplets can be grouped into SO25 multiplets for the massive states. So it all works well. And now we'll discuss. So before passing to the description of the spectrum and conformal gauge, which is our next topic, we will dwell a little bit on some other effect of string theoretic effect, or effect of two-dimensional field theory, if you like, which is called T-duality. So we'll discuss a little bit about compactification. T-duality. So this is some stringy effect that you don't have for point particles. So in general, well, compactification is necessary in string theory because there are extra dimensions. For example, in bosonic string, there are 26 dimensions. So to get to some more physical number of dimensions, you have to compactify the other dimensions. There are various compactifications that you can have, but the simplest one is on a torus. So you just assume that your spacetimes are 1 d minus 2 cross S1. So this is the simplest compactification on a circle here. So it's compactified dimension. So this is a circle of some radius. So this is radius r. And we'll assume that the coordinate here along the circle is the 25th coordinate. So this is so this is kind of 24. So the important difference when you have a compactified dimension as opposed to the uncompactified ones is that the string can wind around this circle, right? And that means that even for a closed string, so we will only discuss this in the context of closed strings. There are similar effects for open strings, but they're a bit more involved. So let's discuss closed strings. And before we always required that all coordinates be periodic with respect to sigma, right? because it's a closed string, so kind of it's natural to have periodic dependence. But now we have we can slightly relax that condition because x25 is a periodic coordinate. So we will say that x25 sigma plus 2 pi by mr, where m is an integer. So it's a circle of circumference 2 pi r, right? So modulo 2 pi r. This is periodic modulo 2 pi r, but that means that the string now winds around that direction m times, right? So there's a kind of this, right, and then it's m. So winding m. So this is x25. And so our Fourier decompositions need to be modified now slightly for x25. More exactly, they take the following form. So x25 yeah, that's it. And yeah, m belongs to z, just as before. So as opposed to what we had before, there is now a linear term in sigma, which says that x25 is periodic modulo 2 pi r. So this is the decomposition we had before. Just before we wrote it out in terms of the left and right modes. Left and right moving modes. Here I just sum it up. And the new feature is this linear term in sigma. So this is the new feature. But the extra term now modifies various other formulas. So in particular, it modifies the mass formula and the level matching condition. So, yeah, remember we had the mass formula, which comes from integrating the constraints, C1 equals 0. So it's one of the constraints. And the other comes from integrating the level matching, comes from integrating the second constraint. So this is from here we get the mass formula. We get level matching. So the modified mass formula reads So this is the new mass formula. So it looks very much like the old mass formula with two differences. So first we've singled out P25, the momentum around the circle, and the winding contribution. There's a winding contribution. And then we can call this P squared. So this is the square of the momentum in the non-compact directions, or maybe with P mu squared. So then we get the modified mass formula, which says that m squared is so this is the square of the mass of the particle propagating in one dimension less. And now, well, I'll explain why we've put the momentum in there as well. But first, let's see how the level matching constraint is modified. So here m is an integer, which is the winding number. Not to be confused with the mass. So the level matching constraint comes from integrating the x minus prime. This is PXA prime. And this gives so the difference of the levels, like we had before. Gives this formula, so there is this extra contribution coming from the winding here as well, because now the derivative of x25 has an extra piece. So that means that the level matching is modified to n minus n tilde plus So of course, for this to make sense, there has to be some restriction on P25, right? Namely that it should be an integer as well. Because, well, n and n tilde are integers. So m is an integer, so this has to be an integer as well. And that naturally comes out because we have a circle and momentum is quantized on a circle, right? Because well, basically, suppose you have a wave function. So I'll just remind you what's the logic behind quantization of momentum. So we have wave function psi of x25 because basically our string is like an infinite dimensional mechanics, right, as we discussed before. So it has a p and x coordinates corresponding to the propagation of the center of mass of the string, which propagates as a particle in 26-dimensional space. And it has these oscillator degrees of freedom, right? So when you quantize it, just the p and x coordinates, you may view elements of your Hilbert space as functions of the coordinates. So just the usual wave functions in quantum mechanics. And momentum becomes an operator acting on such functions. So this is minus I d over dx 25. So the eigenfunction of this operator is just the exponent but then you have the periodicity condition, right? So x25 is identified plus 2 pi r. This is so you shift. So you require psi to be periodic. Which gives you the desired quantization condition that R is an integer as well, R times P25. So substituting this here, we find that n minus n tilde plus mn equals 0. Here m and n, both integers. So one of these integers is the winding number. The other is the momentum in the discrete momentum in the compact direction. Right? I mean, this is a requirement. Require. So now the spectrum of the string compactified on a propagating in a space where one of the dimensions is compactified is described by this formula plus the level matching condition, the modified level matching condition written here. And of course, in principle, you can compactify more directions. In this way, you will get further modification of this formula in a similar way. Okay, so let's also so we were written the level matching condition. Let's also rewrite the mass formula given the discrete momentum P25. So this gives. So this is a spectrum of mass spectrum in this is one of radius r. So this is n over r. So this is the quantized formula. So here I insert, this is the normal ordering constant. So this is the same as A being 1. Plus the level matching condition, which is there. So for example, in the case of a 0-0 winding, when M is 0, this just becomes it's essentially the old formula, just that we've now split the momentum along the 25th direction as a contribution to the mass rather than to the momentum squared, kind of, right? So this is a momentum part. And this is the winding part. And if M is 0, so N is equal to N tilde, so that becomes N minus 1 twice.
So is alpha prime like 1 over 2 pi t or something like that?
Yeah, that's right. That's exactly right. T is 1 over 2 pi alpha prime. Right, we discussed last time that alpha prime is something related to Regge trajectories, the slope of the Regge trajectories, and that's set by the tension. Yeah, alpha prime is also a nicer variable because you have less factors of pi if you use alpha prime. Because precisely because of this relation. Okay, so what is interesting about the spectrum? The interesting thing is that it has a discrete symmetry of interchanging n with m, essentially. All right. So this is what is called T-Duality Symmetry. Which is R goes to alpha prime over R. And M interchanged with M. Right, you see when you interchange M with N, these two pieces are swapped, and if you then R goes to alpha prime over R, then it's completely symmetric. But that's a remarkable formula because that kind of interchanges the small radius with large radius. Right, so due to winding to the winding modes, the smaller radius or large radius compactifications are indistinguishable. And that's the property of two-dimensional field theory, because precisely it's due to the winding. Another interesting observation, which is just kind of an observation, but yeah, let's go, is the property of the lowest mass particle in the non-zero winding sector. So consider n equals 0 and m not equal to 0. So let's see what's the property, the mass spectrum in this sector, so M squared closed, is MR four over alpha prime n minus 1. So because here we've set n equal to n tilde, because n is 0, so n is equal to n tilde. So now if we further set n to 0, so the lowest level, we will get mr over alpha prime squared minus 4 over alpha prime. For large r, this is positive. So this is for large r, for r going to infinity. But you see there is some critical value of r where this becomes 0. So there are some additional tachyonic states in this winding sector. So we know there is a tachyon in the 0 winding sector. But then there could be also additional tachyons in non-zero winding sectors. So this let's call it 0m, so m squared becomes 0 for r so this is the largest value of r occurs for m equal to 1, so this is 2. Let's call it r critical. So for larger values of m, there will be additional states that will become tachyonic for smaller values of r. So as you reduce r, there will be more and more tachyonic states. So interestingly, if you now this is some circle in space-time, right? So we know that field theory at finite temperature can be described by having a temporal circle of radius that's of size being equal to inverse temperature, right? So if we just kind of boldly identify this with inverse temperature, identify if one identifies with a thermal circle, so the radius 1 over the temperature. So this is not to be confused with the tension. This is temperature. Then one finds some critical temperature. T critical, which is 1 over R critical. Yeah, more exactly, this is 2 pi r, because this is our length of our coordinate. So this is 1 over 2 pi r critical, and this is 1 over 4 pi square root of alpha prime. So this is a Hagedorn temperature that we had before. So this is could be thought of as some critical temperature where you get some additional tachyonic states. And the point is that why this is actually different from the usual string tachyon is that the usual string tachyon disappears in the superstring. So there is no tachyon in the superstring, because A is 0 there, and there are no negative squared mass states. But this property will persist in the superstring. So at some critical value of the compactified radius, you will still get some tachyonic states. And that's interpreted as, well, that's related to this divergence of the partition function at this temperature. So it's believed that there is some kind of phase transition when, you know, some particle becomes massless. It's usually a sign of some phase transition and so on. But this is just a curious fact. So this is the main reason I'm talking about this, is to introduce T-duality, and which is one of the interesting features of string theory. Next thing we will do, we will describe how you can see T-duality from the actually string action. So you may wonder, okay, we've derived the spectrum. We've seen it's symmetric with respect to some discrete symmetry. So can you see it at the level of the action, or what should you do to? I mean, could we guess it without doing the calculation? Okay, so let's continue. So, like I said, we are going to discuss the properties of the action, or how to see T-duality at the level of the action. Let's let's assume we're computing the partition function. That which is so here we will consider the theory where we just have one circle. So field theory with one field. With one field, x 25 if you like, or whatever x, we will also call it phi. And we want to compute its partition function, so that's a little bit slight shift from the previous setup. So you have some path integral e to the minus the action. So this is action, and the action has the form that S is d phi d bar phi. So the radius is now explicitly written out here. So the periodicity is phi I plus 2 pi. And yeah, so if we're computing the partition function, so beta is basically, you could think of our Riemann surface here. There's some Riemann surface. You can think of it as the torus, S1 cross S1. So one S1 is of radius beta, and the other S1 of radius, say 2 pi, which is our spatial S1. Okay, so there is this 2 pi periodicity of phi. So notice there are periodicities both in target space and in space-time, right? So these 2 pi is where our sigma variable lived, right? Sigma 0 to 2 pi. And this 2 pi is in target space. So this is a target space circle. And the radius is just explicitly written out here. This action has the obvious continuous symmetry, which is a shift of phi, right? So there is a U1 symmetry, U1 global symmetry, which is phi goes to phi plus alpha. Where alpha is a constant. And now what we will do is we will gauge this symmetry. Okay, so if you have a global symmetry, you can gauge it by introducing a gauge field. So let us gauge this. So that means introduce a gauge field A, which is A dz plus A bar dz bar, worldsheet gauge field. To be clear later why we want to do that. So that means that we replace d phi with the covariant derivative. So d phi becomes d phi minus A. For example, d curly d phi is curly d phi minus curly A. So if we just do this, then we get some theory which is empty, because okay, if we just plug this thing back into the action, then well we have a gauge symmetry. So phi now phi goes to phi plus alpha of zz bar, and A goes to A plus d alpha, right? So in particular, we could just kill the phi field by doing this z-dependent shift. So we could go to set the gauge phi just equal to 0. And then our action will be just the square of A. So in particular, the equation of motion will tell us that A is 0. So this is a kind of silly theory. But of course, that's not really what we want to do. We want to rather get another description of the original theory. So how do we do that? Well, first we want to do some modification of the theory which really doesn't modify the theory. So we've gauged this. We've inserted a covariant derivative here, but now we'll say that the gauge field is trivial. Yeah. So more exactly, that it's pure gauge. So if you introduce a gauge field that's pure gauge, that does nothing to your theory, right? So how do we do that? Well, let's write the action in the following form. So we have this first gauged piece. So this is d phi, d bar phi. But now we'll also introduce a term, theta, which A minus d psi. Right, so here I've introduced some Lagrange multiplier. Multiplier one form. So in this case, this is a one form. So varying with respect to theta. would say that A is deep psi, and then we could shift phi plus psi, and this would remove psi whatsoever, right? So this extra piece tells us that A is a trivial connection. Then substituting it here and shifting phi by psi removes psi. So this is undoes the modification.
Excuse me, can I ask a question? It's quite untimely, but what is S1 beta when we introduce the Riemann surface? I don't know.
Beta is the, well, it was in the parameter of the partition function, right? So, yeah, inverse temperature, beta h, right? So once we compute the partition function, then beta becomes that's the same argument we used in the previous part of the lecture. That inverse temperature becomes a Euclidean circle. Can be interpreted as having a Euclidean circle of radius beta. So yeah. Okay, so adding these terms to the action does nothing really. Okay, but we can do something else with this action. Namely, we can vary with respect to psi. So if you vary with respect to psi, you find that d theta equals 0, right? So theta is a closed one form. So what we can do, let's do something that what we tried to do before, namely to kill phi by a shift of A. So let's do the shift. A goes to A plus d phi. So when you shift A by d phi, there is an extra piece coming from this term here, right? So we get an extra piece, which is theta wedge d phi. And what this actually is an integral over your Riemann surface of a product of two closed forms, closed one forms. Because theta is a closed one form by the equation of motion, and d phi is also a closed one form. It's not really exact, because it has non-zero windings, right? So when we say that phi has some windings, that means d phi, the integral of d phi over various cycles is an integer, effectively. Is 2 pi n. So that means that actually this is not an exact. It's not an exact form. It's just a closed form. And for a product of two closed one forms, there is what is known as Riemann bilinear identity. Which says that this can be computed as a product of in the following way. So you compute the windings around various cycles. So this is valid for arbitrary Riemann surface. Here we're considering a torus. So A and B cycles are just the, so this is a torus. And so the A and B cycles are the two sides of the, say this is A and this is B. The two homologically non-trivial cycles of the torus. If you have a general Riemann surface, you have more homologically non-trivial cycles, but then you sum over all pairs of such cycles. And now this can be written as, so 2 pi nm prime minus 2 pi mn prime, where n and m are the windings of phi around the two cycles, and m prime and n prime are the windings of theta. So m prime is yeah, this formula, by the way, it can be easily proven by Stokes' theorem if you work in this square. So a square is simply connected, yes. So here everything is, or exact forms are, or closed forms are exact. So you integrate over the square, and then the integral boils down to the integral over the boundary, and then you remember that actually so basically these integrals over A and B cycles, they come from integrals over the boundary. So you can just prove it like that. And then, so the windings of phi are n and m, 2 pi n, 2 pi m, because phi has periodicity 2 pi. And m prime and n prime are just the definitions. These are the windings of theta. Okay, and now, so phi has almost disappeared from the action, apart from the fact that it contributes this integer, these integers. Right? The rest of phi has disappeared from the action. But when computing the partition function, we're meant to sum over all these winding sectors. So we're actually summing over n and m. And these sums will produce the following. So z over all winding sectors. Means so that means that you have sums like this. And what does this tell you? So what is this sum, roughly speaking? So this is a periodic delta function, right? So it says that m prime, says that m prime is an integer. So if m prime is not an integer, then the sum is 0. If m prime is an integer, then this is infinity, strictly speaking. But if you think more accurately, you realize that it's a delta function. So that's just an identity coming from Fourier decomposition. Yeah. So kind of completeness of the Parseval identity for Fourier series. Yeah, completeness of Fourier series. This tells you that m prime and n prime accordingly are integers as well. So a priori, the windings of theta are just real numbers. So this is a one form. It can have arbitrary windings. But summing over these topological sectors for the phi field actually gives you a delta function saying that these real numbers are integers. So yeah, so in fact, you could as well write theta as basically d psi, where psi is a, so that means that kind of theta is d, or maybe let's call it phi tilde. Right, where phi tilde now has periodicity 1. When we say it's d phi tilde, it doesn't mean it's an exact form, right? It's just a notation, because okay, so and then we solve, the final step is we solve for A. So solve the equations for A. So our action becomes this just A bar plus integral d phi tilde wedge A, right? So we can now eliminate A from the equations. So psi, we treated psi as a Lagrange multiplier, saying that d theta is 0. And we parameterize theta as d phi tilde, d of phi tilde. And now we eliminate A. So the equations for motion tell you that A is minus 1 over r squared d bar phi tilde, and A bar is d phi tilde. I guess I'm assuming I put an I here. So then you substitute back in the action. And so when you substitute, you get that this is so you see we get the same action basically as before, but with an inverted radius. So the radius now stands in the denominator, which is, as we know, is what we should get, because r is replaced by 1 over r, essentially. So more exactly, the map is r squared to yeah, so here phi tilde has periodicity 1. So this can be written as d to z 1 over 2 pi r squared d lambda d bar lambda, where lambda now has periodicity. Lambda is 2 pi phi. And this is identified with lambda plus 2 pi. So we just introduce a variable which has the same periodicity as the original variable. That is to say 2 pi.
Sorry,
Uh-huh.
can you repeat? How did we understand that delta equal differential phi?
No, it's just a notation, if you like. I mean, a form. You have a form whose winding is an integer, right? So that looks like a differential of some angular variable because the angle has periodicity 2 pi, yes? So here we introduce some angle which has periodicity 1, and if the form is differential of that angular variable, it will have periodicity 1, therefore, right? Same like one form d phi on a circle. It's not exact, right? It's closed, but it's not exact, but we'll still write it as d phi. But it has a non-zero holonomy around the circle, right? The integral is non-zero. So it's just a standard notation for when you have angular variables, basically.
Can you also explain again why we can set d psi to 0 in the second integral?
Why we said no? I mean, we use psi as a Lagrange multiplier, whose equation of motion gives you d theta equals 0. So in the integral, it's a delta function. So, in the integral giving the partition function, imagine you've integrated over psi. It just gives you a delta function of d theta. So that's it. We don't set it to 0. We vary with respect to psi. Yeah. Okay. So the map. So the map here is r squared goes to 1 over 2 pi r squared. And in string theory notation, the one we had before, r squared is 1 over 2 pi alpha prime. So this was our tension. Yeah, so that means that this guy says that 1 over 2 pi alpha prime goes to 2 pi alpha prime over 2 pi squared, which is alpha prime over 2 pi, which means that alpha prime goes to 1 over alpha prime, which is what we got before. I mean, in the description of the spectrum. Okay, so this is the path integral derivation of the T-duality thing. So we've shown that a theory of a two-dimensional field theory where your field is a periodic field is equivalent to the analogous field theory where the radius of this field is inverted, or the period of this field is inverted. Roughly speaking, r goes to 1 over r. There are some 2 pi factors and so on. So the interesting thing, I mean, why this is useful is that this can be generalized to more complicated backgrounds. In the case of the free field taking values in a circle, basically we don't need this path integral derivation. I mean, we've described the spectrum explicitly and we've seen it there. But this kind of derivation can be generalized to arbitrary backgrounds with an isometry. So this is actually what we've been doing here is that we've been describing some elementary sigma model, right? So this guy was sigma model. So it means some field theory related to maps from some worldsheet to target space. So in this case, target space for that was S1 of radius R. But now we could, so in the string theoretic setup that we were dealing with before, we were actually discussing maps from sigma to R1 d minus 2 cross S1, for example, right? But nothing can prevent us from considering just general maps to a general manifold with some metric, right? So, so this can be generalized to maps from sigma to some general manifold M called target space. And this is actually useful also in the string theoretic framework. So in the string theoretic framework, that means that the string is propagating in some space M with some possibly non-trivial metric, curved space, and so on. So we don't necessarily have to consider flat target space, but we can consider curved target space. Of course, it's going to be much more complicated because that means that your two-dimensional field theory in general will be an interacting field theory, right? So what we've been dealing with before, when you have flat target space, then as a two-dimensional field theory, it is a free field theory. But if you consider curved target space in general, it will be an interacting two-dimensional field theory. But nevertheless, one can do that. And let's assume, so M has some metric, so manifold with metric G. Metric G. And two-form field. Field B. So, so you see, if we have a two-dimensional field theory of this type, it is natural not only to consider a symmetric field G, but also a skew-symmetric field B. Why that's natural? Because, well, the action is integral d to z, say G mu nu d alpha x mu we could say, okay, let's assume this is Euclidean. This is dx mu d bar x nu plus integral over two form, some integral over two form. Right. So apart from the symmetric part, we can have a skew-symmetric part, term involving a skew-symmetric field. So in component form, this is just proportional to d to z b mu nu something like that. Right. So if we want to have an action with two derivatives, two worldsheet derivatives, we could as well just add that term. Not only the symmetric term, but also the anti-symmetric term. So this is B field, and it's not a coincidence that this B field also arose in the description of the string spectrum. So you remember when we discussed the massless spectrum of the closed string, just at the beginning of this lecture, we encountered, apart from the metric, we encountered the B field and the dilaton. So we'll forget about the dilaton for the moment, but somehow this is the same B field that appeared there. So that's maybe we'll discuss it a little bit later. That's the concept that might be a little bit difficult to grasp, but basically the idea is that we've been describing the free string. So the free string is a infinite collection of particles propagating in, say, 26-dimensional space, right? The infinite collection of fields. And in particular, it has the graviton field, the B field, and many other fields, massive fields. But once you turn on interactions, as a field theory, these fields start to interact. And for example, they describe interacting gravity. And so that interacting gravity is no longer is described by a flat metric, right? It curves the space-time, so the metric becomes curved metric. And so this could equivalently be described as a non-trivial background of your sigma model. The curving of space, or the non-trivial background values for various fields. So once you have non-trivial background values of your fields, you could as well consider this theory like a sigma model with a non-trivial target space. So that's a kind of dual interpretation. But anyway, now we're not really talking about that. We're just looking formally at this action. And let us assume that this action has this target space has an isometry. So like an analog of our circular variable phi. So assume isometry. So some angle phi that goes to phi plus alpha. So in other words, we have a vector field V, which is d over d phi, and we want this to be a Killing vector. So we want the Lie derivative with respect to V to preserve the metric and also to preserve the B field. So we've now generalized that elementary theory with one variable phi, angular variable phi that we had here, to a complicated theory with many fields, okay? But one of them is phi, and we want there to be a symmetry of shifting phi. So that means that the action, so it's, well, you can prove it, that in this case, the metric can be written as and by the way, before I write the metric, I should say that once you introduce the B field, basically all you have to do is to say that this action can be written as d to z e mu nu dx mu bar x nu. So this is just some tensor without symmetry properties. Right? Its symmetric part is G, its anti-symmetric part is B. So we're just writing the most general quadratic form in these dx mu, d bar, x nu variables. So you can either split it into G and B or just consider an action of this form. So the next step we do is we require this theory to have a symmetry of shifting phi. This means that this action can be written as g phi phi d phi d bar phi m phi a d bar d phi d bar x a plus m a phi dx a d bar phi. And maybe I'll call it M because be called M mu. Then those. So here, all these guys, they do not depend on phi. So they depend on x, but not on phi. In this case, clearly there's a symmetry of shifting phi, right? And like I said before, so m phi a is g phi a plus b phi a. M a phi is g a phi plus b a phi, which is g phi a minus b phi a, because b is antisymmetric. This is the split I was referring to earlier. Okay, and now, so this is well, the claim that whenever you have an isometry, you can always bring your metric to this form where phi only enters via derivatives. Okay, and same with the B field. So now we have a symmetry of shifting phi, and we can do exactly the same thing we did before. Namely, we gauge the symmetry, and then we set phi to 0 and eliminate the gauge field. Right. So the next step we do is we gauge gauge the U1 symmetry. Symmetry phi goes to phi plus constant. And that means that we replace d phi minus a, and we introduce that that extra Lagrange multiplier that says that this gauge field is trivial. But then we shift a by d phi. And this will give those winding terms. So this will give a piece containing the winding terms of phi, which when you sum over these terms tells you that the windings of the dual angle are integers as well. So we introduce some theta with the Lagrange multiplying saying that a is exact. Then that psi that was there, the new variable psi, that will be a Lagrange multiplier saying that theta is a closed form. So you repeat basically everything we just did. And in reality, this procedure just tells you that you can set phi to 0, and just remember that the new variable, new theta can be written as d phi tilde, where phi tilde has integer windings. And then you integrate over the gauge field, and you get a new geometry of the target space. So our action is d to z, which is a bar plus m phi a d bar xa plus m a phi dxa times a bar plus mab dxa d bar xb plus well, I call it lambda here, so lambda times d bar a minus dA bar. So that's effectively what you get. Or maybe I should write this as bar lambda a minus d lambda a bar. Yeah. So that's what you get once you set phi to 0 or gauge away phi. And now you eliminate a. Which means you solve the equations of motion for a. And substitute back in the action. So the action, once you substitute the new values of a, will have the form twirl d to z. MAB minus 1 over So that's what you get upon eliminating a. So you invert this quadratic form. That's why g phi phi goes in denominator everywhere. So you again get some geometry. So you get an action similar to the one we had before, meaning that it's still a quadratic form in dx d bar x, but the value of m is drastically different now, right? In particular, you can read off from this the new values of the metric and B field. And this will be this means that the new metric is the old metric minus the following combination, GA phi, GB phi minus MA phi, B phi. I want to say this is B. Yeah, and B tilde. B is BAB. BA phi, GB phi, minus GA phi, B phi. And G tilde A phi is 1 over G phi phi, BA phi. So these transformation properties are called Buscher rules. For T-duality. So that means that somehow the two sigma models with different target spaces, with different metrics and B fields, they are equivalent. And the transformation properties between these equivalent models are like this. So of course, if you set set B to 0 and assume that G is just a diagonal metric, then you see that also this should be G tilde phi phi is 1 over G phi phi. You see that this is the analog of inverting the radius. So if G phi phi vanishes somewhere, then the new geometry may actually be singular, right? So G phi phi is the square value of the norm of the field d over d phi. So the requirement for not having some singularity in the T-dual geometry is that G phi phi nowhere vanishes, which means that the vector field nowhere vanishes. So dual geometry is non-singular if G phi phi does not vanish. So that means that d over d phi does not vanish. So that effectively means that this is a free U1 action. U1 action is free. So if U1 action has some fixed points, then those fixed points will become singularities of the dual geometry. So, for example, if you consider a torus, the U1 action is free, the one that acts by rotating one of the coordinates of the torus. If you consider a sphere, U1 action is not free. I mean, the U1 action of rotation around an axis is not free because it has the poles as the fixed points. So in that case, the dual geometry will be singular. So I think that's it for today. So we discussed this T-duality, which arises when you compactify target space on a circle or multiple circles on a torus, and generalization to arbitrary target space geometries. And next time we'll pass over to the description of the spectrum of the string in conformal gauge. Okay, so that's it for today.